Hey, welcome back, my neighbors. I know I've been away for a while, but let me assure you, today's video was well worth the wait. And if you look up in my background, maybe you can guess what this video is going to be talking about. Now, the reason why I've been away for a while is because I was doing the necessary research and experimentation for this video to make sure that everything I show you is as accurate as I can possibly make it. So let's get into what this is. So in the last several videos, we had concentrated on capacitors and inductors, and I decided to take one more look at capacitors before we move on to another topic. And in this episode, we're actually going to talk about one particular application of the capacitor. And by looking at what's in the background, you might have guessed this is about something about sound. In particular, we're going to talk about microphones. Yes, that's right. Microphones are actually made with capacitors. And let's get into that. So let's break down what a microphone really is. A microphone is what we call a transducer. A transducer is something that converts, a device that converts one form of energy into another. And in the case of a microphone, we're converting sound waves into electrical impulses, electrical energy, right? And part of doing that, the microphone has certain parts which are important. One, it has a diaphragm, and that's where the sound waves push against. It's a very light film material that is light enough such that even a sound wave as you know, your voice or something very low powered can vibrate this diaphragm. Okay? And behind the diaphragm, or should I say attached to the diaphragm in a clever way, is a capacitor. There is actually is actually separated by an air gap is these two plates. One plate forming the diaphragm and the other plate what we call a backing plate, right? And so the idea is when the sound waves strike the diaphragm, the two plates of the capacitor are moving closer and farther away from each other. And when that is actually the backing plate is connected, it's like a terminal of the capacitor. When it's fed into an amplifier, that signal can be read as output. So this is just a transistor, or in many cases, a field effect transistor. So what do we have here? It turns out that we have to know, in order to know the mechanism of why microphones work, we have to understand another aspect of the capacitor, and that is how capacitance is generally described. Okay, what causes capacitance? Well, the truth is that capacitors are all different sizes and shapes, but what makes the difference inside a two-plate, or it could be a multi-plate capacitor, but it is the construction of the capacitor that gives rise to the level of capacitance that the capacitor has. And the formula for that is capacitance is equal to E times A over D. Now, where E is something to do with the material that is sandwiched in between separating the two plates, it's called the permeability of the material. And A is the area of the plates in meters squared, and over D is the distance in meters over the between the two metal plates. So that gives rise to the capacitance. And as you can see, capacitance is increased depending on, well, the permeability of the dielectric that's in between, and also is related to the area over the distance. Now, as you can see, the area of a capacitor can never really change. That's just how it's built, right? These two plates are a certain size, and there will always be a certain size. That's not going to change, right? But what we can see is that in the microphone, the distance between the plates is the primary thing that does change, all right? So when the sound wave hits the diaphragm, and we can treat this part of the capacitor, the first plate here coming in, as the diaphragm, and as it moves closer, as it vibrates really with the sound wave hitting it, it gets closer and farther from the backing plate. And you can guess, I mean, you don't even need to guess. You look at this formula here is, if E and A are constant, what happens when D varies, right? So you can see, because it's on the bottom of the fraction here, is that the capacitance is inversely proportional to its distance, meaning that the closer the plate gets, the distance is smaller, and therefore the capacitance increases. And inversely, that's true. When the distance between the plate gets further apart, right, the distance becomes greater, and when the fraction in the bottom becomes greater, then capacitance drops, right? But there's something else we have to describe. Now, there's another fact we have to look at. This equation here. Q is equal to C times V. Q is the charge on the plate. So these are the charges on the plate. They could be positive, and on the opposite side we have negative, right? That's the amount of charge. This describes, Q defines the amount of charge that's on the plate. And that is equal to capacitance times the voltage, all right? So as you can see here, that if capacitance in a microphone, we know that the Q, the charge, remains relatively constant. Okay, that's not going to change. The sound does not vary the charge in any bit. Okay, what is being varied here is the capacitance, right? And voltage is the output that we want to see electrically, right? And so what happens is, if the charge remains constant and it is the capacitance that varies things, then in order to make this equation consistent, you can see that voltage must vary. So if you rewrite this one the other way, so Q over C is equal to V, right? So as you can see, as capacitance is inversely proportional to the voltage, all right? So as capacitance rises, the voltage becomes smaller. And as capacitance decreases, then voltage becomes bigger. So what do we have here? This is basically your generic dollar store Android headset, okay, with a microphone connection. So here you can see the earbuds, and the microphone is here. There's a little hole, okay, and the way it connects, okay, with this connector. And if you can see, I've cut it off because I wanted to do we're going to do some probing with this one, right? So there are several conductors. This is really cool, is that there's several conductors in the single wire, okay? It's actually 4 wires, but look at this single this is single plug. It actually has a separation between 4 separate conductors. This is called, the end conductor here is called the tip, separated by a plastic here. There's another conductor in the center, I guess the right center here, which is called the ring. And then there's another ring right beside it. And then the last conductor, the largest one on the outside, is called the sleeve. So basically there are 4 separate conductors, and each one has a special function. In this particular instance, the last ring on the left here is actually the ground signal. It's a common ground between all the 3 other conductors. This one on the far right is one of one of the headset earbuds. So maybe your left side, your left audio signal. The next one is your right audio signal. And then the one here is, like I said, is the ground. And the other one here is the sleeve, which is your microphone signal. Let's take a look at how this is interfaced. So I had cut all these wires off. I had cut the connector off so I can easily basically hook this up. Now, let me describe what's going on here. What I've done here is on the microphone signal wire, which is coming out of this black wire here, I've attached 2 resistors in series. I put 2 5K, 5K6 resistors in there. So this gives about 10Ks of resistance, right? And I'm going to attach a voltage source here, a DC power source to this end of the resistors, which will give power to the microphone's amplifier. The other part is here, before the resistors, like between the resistor and the microphone, I've also put in a 0.1 microfarad, capacitor on there, and I've left the output to be free. So this is your AC coupling capacitor, and I'm going to read the output off of here, right? So without this capacitor, I would be reading the DC portions as well, which I don't want. So I'm going to put this here, and I'm going to attach this to the oscilloscope, and you should see how this is working. And of course, the ground wire will be connected to basically this conductor here. It's hard to see, but there's another conductor. Actually, that is the wrong one. It is this one, actually, right here, this conductor here. Okay, I'll attach this one to the ground wire, right? And then we should be able to see the signal on the oscilloscope. So now I got this hooked up, and I've got the oscilloscope on to normal capture mode. So if I make a sound on the microphone here, let's talk into it. I'm gonna say something to it. Hello. You can see the oscilloscope responding to that signal. All right. Now, to give you an idea of how different sounds look like, I'm going to use that the xylophone that I had and play a couple of notes on it, and you can see. It's better than me talking into the microphone like this, because human speech doesn't give it may give a regular pattern, but playing notes like A, B, C's, and D's have a well-defined frequency, and it's much easier to see them on the oscilloscope. So let's do that. Okay, let's see what we got. Let's play a note and let's capture it. Okay, as you can see, now we can put our measurement rulers, these 2 big lines, onto both of the peaks, because this measures if you set it exactly on the start and the end of each beat on the signal, you can actually measure the frequency of the signal. So for example, this reads here, this note that I played is 5.814 kilohertz. Okay, so let me play a much lower note, and we'll see what we get from there. Okay, so now I'm going to play a lower note. Yes, I mean, it's a little bit of a trick to capture it on the oscilloscope, but that was a much lower note. And let's put the guide rulers where we are. Okay, I'll put it on both of the peaks so that we know it's one cycle here. Okay, so now we measure 2.5 kilohertz. Okay, so different sounds, different musical notes have a well-defined frequency, right? All sounds that we hear are basically just beating at a different frequency, okay, and different intensity. levels. So that's the pitch of the sound is basically the frequency. Okay, in certain pitches or frequencies, different musical notes have different frequency and pitches, of course, right? So that's what we're capturing here. Let's just to try it again. I'll put a higher frequency note again. Once again, let's play a higher note. Okay, this was the lower note. This is the higher note on the xylophone. Let's play this one. Let's measure that. Oh, it went away. It captured another one. So these bars, let's measure the peak. I mean, it's hard to see, but to measure this, this is 6.4 kilohertz, much higher than the previous one. So what I'm hoping to show you is that, of course, this works. And this microphone is essentially a capacitor, using a capacitor as a transducer. Very, very interesting. So now you have a basic understanding of how the microphone works. At least this is how a class of microphone called the condenser microphones or capacitor microphones work. Now you've been maybe wondering about this line coming into here onto the diaphragm here. Well, this is an implementation thing. All condenser or capacitor microphones will have this power line fed directly onto this plate of the capacitor. After all, if there is no positive charge or if there's no charge at all on this plate, how can the vibration of the capacitor actually induce an alternating current here? Well, the answer is that it cannot, right? And if you imagine that any wires attached to a diaphragm will just impact its performance, its vibrational performance, right? The range of signals of sound waves that it could produce, that it could catch, will be very small, right? You would need a big powerful sound wave to make this vibrate in a bit. Now, don't get me wrong, like these condenser microphones work very well, and right? The secret is in the implementation, how well you can do it, right? But it turns out that the reason why microphones these days are so cheap and everybody has them and they're so accessible is, I think that is owed to the fact that in 1962, two men, one James West and Gerard Sessler in Bell Laboratories, invented what's called the Electret microphone. Basically, what that means is getting rid of this power line into the diaphragm. What they've invented, or they pioneered using, electrets were invented far longer and known far longer than that, far before 1960. But they pioneered the use of putting the electret material onto this plate of the capacitor, right? So essentially getting rid of that power line. What they've done is they've used an electret material. Basically, an electric material is like this, right? It's basically a material with a charge that is made permanent or semi-permanent, or what they call quasi-permanent. Okay, so imagine this is the diaphragm of the microphone, and this is the backing plate, right? And what they've done here is this particular material is permanently charged. The orientation of the charge is made permanent and fixed, right? So while on one surface you may have a negative charge here, and on the other surface, you will have a positive charge. And through the process of making this electret material, these charges become fixed in position. So it's like this, right? Negative, negative. And this is what they call a dipole material, okay? It has two poles. Now, when it's like this, effectively, as the diaphragm moves closer and farther from the backing plate, this positive charge here, it never switches position with the negative, right? It's made permanent this way. And so the opposites attract and similars, right, repel. We all know that, right? So here on the plate, this charge is free. It's allowed to move like in any conductor. So as this positive gets closer, right, the tendency is for negative charges to build up here, right? So more or less, the charges will build up more or less depending on the vibration here, right? And that's what causes the alternating current to move through this signal wire, right, with that movement. But the genius here is that the electret material allows this to happen because there's a permanent charge. Now there's no longer a reason, or there's no longer a need to permanently polarize or charge this capacitor, because it's already this plate is already permanently charged. And that's the genius of this. Without this wire, you can imagine the implementation of this becomes so much more simple, and the sensitivity, the sounds range that this can pick up, because this film is essentially allowed to vibrate as freely without anything connected to it. This makes the implementation of good sounding microphones very simple. And in fact, the construction, if you see any diagrams of this on the net, you will see the implementation of this is so simple that is the reason why microphones and headsets are so accessible today and so cheap. That's why I got this thing from the dollar store for less than $2, right? So this is a very important innovation. It was done in 1962. So now, guys, I know maybe you might be thinking, hey, is this electric material actually created an infinite power source? After all, we're creating voltages here, right? And somehow that voltage can move speakers and other devices like that. Well, I assure you, there's no infinite power source here, and I'll prove it. Okay, my neighbors, this is the proof that no matter how much this seems like an infinite power source, it is not. First of all, there's two pieces of this thing. First is the microphone device itself, right? And the second is the sound wave. First of all, the sound wave requires energy to generate. So that takes care of half the problem, right? We already know that you need a source of energy to produce the sound in the first place, right? So already, this is not a free energy device. Second of all, even if you discount that, you think this microphone, this electric, oh, it's permanently charged, it generates voltage and there's a current flowing through. Well, I said there was a current flowing through, but how much, right? There is very little current flowing through, and the reason why this works is because of this transistor here is actually called is a JFET. It's a junction field effect transistor, which means the operation of the gate is entirely based on voltage, and current is basically voltage and charge. It is not a current-based device. In fact, if you measure the impedance between the gate and the source here, it would almost be infinite. Okay, there's literally, you can say practically, in all practical sense, there is no connectivity between them, even though there is a little, but there is no connectivity between them, right? So what happens is this junction field effect transistor does not work on the principle of current flowing through. It is actually detecting, it is able to discern the difference between the charge on the source and also the charge applied at the gate. So basically, it just says whenever the polarity doesn't matter. There's different JFETs. There are enhancement type JFETs and there's depletion JFETs, right? The P channel and N channel. There's two different types, and that just sets the polarity. But let's just say this: it knows the difference between the potential between the source and the gate. And so what happens is that when you have the diaphragm moving in and out, moving this positive charge closer to here, basically what happens is these are the molecules or the atoms on the conductor here. What happens is that the charges just reorient themselves. So the electric field between them, okay, you know this side will reorient itself to be negative, right? And there's a movement there. The charges actually do flip over. So on this side, it will be more likely to be positive, this side. It's pushing, basically, as the positive charge gets closer to this plate, right? The negative charges would like to attract and move towards the positive charge, and that's why on the left side of the plate is all negative. But again, this charge does not come from nowhere, right? The molecules, the atoms on this conductor already contain the charge. It is a neutral charge because it's balanced, right? There's a positive and negative. But as this positive charge gets closer to this side, its basic nature will be to move, to reorient itself such that the negative charges are closer to the positive ones. And therefore, on this side, the positive charges will end up on the gate. When the junction field effect transistor sees that there's a potential difference between the source and the gate, this will vary the channel width inside the transistor, which will allow it to vary its electrical resistance, right? Of the drain and the source. So basically, I hope I've convinced you here that now that although how clever this device is and how little power it requires, virtually none, that this is not a free energy device. It does not generate any usable energy. Okay, and the secret to that is this is a field effect transistor. This will not work using a BJT transistor simply because there is not enough current here to operate the gate on a BJT, right? It only works on MOSFETs and JFETs. So I hope I convinced you that this is no free energy device, and in fact, there is no free energy device in this universe, all right? So at least we don't know so far, all right? Okay, over to conclusions. We learned a lot today, and I think by looking at the microphone, we learned a lot about capacitors as well, even more in depth about capacitors, right? We learned that the charge is equal to the capacitance times the voltage, because in the microphone, we keep the charge constant and we vary the capacitance. And as we vary the capacitance, the only thing that's forced to change here is the voltage, right? Now, the way the capacitance change in a microphone is because the capacitor itself, the geometry of the capacitor itself actually changes. In particular, the distance between the two plates changes. And as the distance changes, the capacitance changes. So the capacitance is inversely proportional to the distance between the two plates, right? Now we also learned that electrets are pretty cool. but they are definitely not free energy devices, right? And in fact, we learned that the reason why this all works without actual energy being transferred is because the transistor itself being used has a gate which doesn't conduct any current, no useful current anyways, very so little and very so small, right? This is a field effect junction transistor, JFET, which is used in microphones, and its impedance is so high that no current can flow through. In fact, its basis of operation is entirely on voltage and the charges. Okay, so we've learned a lot today, and if you like this video, please like and subscribe. And in the next video, I think what we can do is, now that we did this, I think there's an interesting experiment we can do with field effect transistors that really show that field effect transistors don't take any current to operate, and it's purely based on the electric field. Okay, so if you like this video, again, please like and subscribe and wait for the next one. It should be very interesting. Have a nice day.